In this video, we shall discuss the condition for existence of inverse of a matrix. Now, to find the inverse of a matrix, we shall first define adjoint of a matrix. Now, what is adjoint of a matrix? The adjoint of a matrix A, square matrix A, equal to Aij of order n by n is defined by the transpose of a matrix capital Aij of order n by n, where capital Aij is the cofactor of the element Aij. Adjoint of a matrix A is defined by ADJ A, or you can say adjoint A. Now, what this means is that in order to find the transpose of a matrix, first of all we will find out the cofactors of elements of a matrix, and then we will find the transpose of the cofactor matrix to find out the adjoint A. Now, suppose there is a matrix A of order 3 by 3. Now, in order to find its cofactors, its adjoint, first of all we will find out the cofactors of the element, and the adjoint of A will be equal to transpose of cofactor of matrix of elements of A. And as we know, the transpose of a matrix is obtained by interchanging its rows and columns. So first row of the cofactor matrix will become the first column of the adjoint A, and second row will become the second column of the adjoint A, and third row will become the third column of the adjoint A. Now, there are some theorems related to adjoint of a matrix. Now, first one is, if A be any square matrix of order n, then matrix A into adjoint of A is always equal to adjoint of A into matrix A, and that is equal to determinant of A into identity matrix. Now, second one is, the square matrix A is said to be singular if determinant of A is 0, and it's said to be non-singular if determinant A is not equal to 0. Third point is, if A and B are non-singular matrices of the same order. If there are two matrices A and B and both are non-singular, then A into B and B into A are also non-singular matrices of the same order. The determinants of the product of matrices is equal to the product of their respective determinants. That means, if we find the product of two matrices and then after that we take their determinant, then that will be equal to the product of the determinants of matrices. Suppose there are two matrices A and B. For them, the determinant of A and B will be equal to determinant A into determinant B, and A and B should be the square matrix of the same order. Now, last point is, a square matrix A is invertible if and only if A is non-singular matrix. That means we cannot find the inverse of a singular matrix. Now, inverse of a matrix, suppose for matrix A, inverse of matrix A will be given by A inverse, and this can be obtained by dividing the adjoint of a matrix with its determinant. In exercise 4.5, in first and second question, we have to find the adjoint of each of the matrices. Here I am solving the second question. Now, in question 2, the matrix is given to us and we have to find its adjoint. In order to find the adjoint of a matrix, first of all we will find out the cofactor of the element of its elements. Now, cofactor of the first element of first row, that is A11, will be equal to minus 1 raised to power 1 plus 1 into minor of 1 1, and that will be minus 1 raised to power 1 plus 1 will give us the positive sign, and you can say that will be equal to plus 1 into minor of 1 1 1. Now minor of 1 will be obtained, this first element will be obtained by eliminating its row and column, and that will give us determinant of 3501, 3501, and that will be equal to 3 into 1 will be 3 minus 0 into 5 will be 0, that will be equal to 3. Now similarly, A22, that is minor of second element of first row A12, minor of second element of first row, and that will be minus 1 raised to power 1 plus 2 minor of 1 2. Minus 1 raised to power 3 will give us the negative sign into minor of 1 2. Now minor of second element of first row, that is minus 1, will be obtained by eliminating the row and column of minus 1, and that will give us determinant of 2 5 minus 2 1, 2 5 minus 2 1, and this will be equal to minus 2 into 1 will be 2 minus 2 into 5 will be plus 10, and that will be minus 12. Similarly, we can obtain the minors for other, or you can say cofactors for other elements of the matrix. Now A32 will be equal to minus 1 raised to power 3 plus 2 m minor of A32. Now A32, that means we are finding the minor of 0, and that means we have to eliminate the row and column of A32, and that will give us determinant of 1 2 2 5. This will be determinant of 1 2 2 5, minor of 3 2. Now minus 1 raised to power 5 will give us the negative sign, and that will be minus 1 into 5 will be 5 minus 2 into 2 will be 4, and that will be equal to minus 1. Similarly, A33 will be equal to 5. Now the adjoint of A, or you can say adjoint of matrix A, will be equal to transpose of cofactor of the matrix, that means transpose of A11, A12, A13, A21, A22, A23, and A31, A32, A33, and that will be equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. Now I will put the values of the cofactors. A11 was equal to 3, A21 was 1, A31 was minus 11, A12 was minus 12, A22 was 5, and this was A32 was minus 1. Now A13 was 6, this one was 2, and A33 was 5. So this is our adjoint A. In second question, we have to prove that A into adjoint A is equal to adjoint A into A, and that equal to determinant A into I. So in these questions, first of all, we will find the determinant of A, and then we will find out the adjoint of the matrix. After finding the adjoint of the matrix, we will multiply the matrix A with adjoint A, and then adjoint A into matrix A, and these two will give us the same result as we will, and at last, as we get on multiplying determinant of A with the identity matrix. Now always keep in mind that the identity matrix here will be of same order as that of the matrix A. I am doing fourth question. Here matrix A is given to us. Now first of all, we will find adjoint determinant of A. Now determinant, I am finding the determinant of A by expanding second column, as here the two elements are 0. So it will be easier to expand the second column, and that will give us minus 1 raised to power 1 plus 1, 1 plus 2 for minus 1 into determinant of, on inverting the row and column of minus 1, we will get 3 minus 2 1 3, 3 minus 2 1 3. Now plus minus 1 raised to power 2 plus 2 into 0 for the second element of second row, you can say second element of the second column, into determinant of 1 2 1 3, plus minus 1 raised to power 3 plus 2 for the third element of second column, into 0 into determinant of 1 2 3 minus 2. Now this will give us minus 1 raised to power 3 will be equal to minus 1 into minus 1 into determinant of 3 minus 2 1 3, that will be 9 plus 2, plus, now here these two elements here they are multiplied with 0, so they will give us 0, and this will be 9 plus 2 will be 11, 11 into minus 1 into minus 1 will be equal to 11. So 11 is the determinant of the matrix A. Now we have to find the adjoint of matrix A. For that, first of all, we will find out the cofactor of the matrix A. Now here I am directly finding out the cofactors of the matrix. You can find the cofactors as we have done in question number 2. Now here first element, cofactor of first element will give us the minus 1 raised to power 1 plus 1, that will be positive. Second element, now first element will be positive, and this will be the into minor of the first element, and minor of the first element will be obtained by eliminating row and column of the first element, and that will give us 0 minus 2 0 3, and this will be 0 into 3 will be 0 minus 0 into minus 2 will be 0, and that will give us 0 plus 0. Now second element of the first row, that will be minus 1 raised to power 1 plus 2, that will be negative, and this will, and for minor of minus 1 will be obtained by eliminating its row and column, and that will be 3 minus 2, determinant of 3 minus 2 1 into 3, and that will 3 into 3 will be 9, minus 1 into minus 2 will be plus 2, 9 plus 2. Now third element of the cofactor will be minus 1 raised to power 1 plus 3, and that will be positive, into minor of 2, and minor of 2 will be obtained by eliminating the third column and the first row, and that will be 3 into 0 3 0 1 0, determinant of 3 0 1 0, and that will give us 3 into 0 will be 0, minus 1 into 0 will be 0, 0 minus 0. Now similarly we can proceed to find out the cofactor of the elements of second row. Now cofactor of 3, that will be minus, no, 3 is this first element of second row, minus 1 raised to power 2 plus 1 will give us the negative sign, and on eliminating its row and column we are getting determinant of minus 1 2 0 3, and that will give us minus 3 minus 0. Similarly for 0 we will get 3 minus 2, and for the last element of the second row it will be minus 1 raised to power 2 plus 3, that will be negative, and for minus 2 the minor will be 0 plus 1. Now first element of the third row, that will be minus 1 raised to power 3 plus 1, that will be positive, and the minor of 1 will be obtained by eliminating the row and column of 1, and that will give us determinant of minus 1 2 0 minus 2. So this will be minus 1 into minus 2 will be 2 minus 0. Now second element will be negative, third row will be negative, and this will give us the determinant of 1 2 3 minus 2, that will be minus 2 minus 6. And third element will be positive, that will give us 0 plus 3. Now here I have obtained the cofactor of the matrix directly. Now you can also find out A11, A12, A13 and so on, as we have done in previous question, and then you can write the cofactor of a matrix A. Now this will be 0, minus 11, 0, 3, 1, minus 1, 2, 8, 3. Now these are the cofactors of elements of matrix A. Now adjoint of matrix A will be equal to transpose of A, and that will be equal to transpose of A will be equal to, now first row of cofactor will become the first column of the transpose, that will be 0 minus 11 0, second row was 3 1 minus 1, and third row was 2 8 3, and that will be the third column. Now this is the adjoint of matrix A. Now we have to prove that A into adjoint A equal to adjoint A into A equal to determinant of A into I. So first of all we will find A into adjoint of A. Now that will be equal to matrix A was 1 minus 1 2 and 3 0 minus 2 1 0 3, and determinant of A and adjoint of A was 0 3 2 minus 11 1 8 and 0 minus 1 3. Now on multiplying A into and adjoint A, we are getting the value as 11, matrix whose diagonal elements are equal to 11 and other elements are equal to 0. That means we are getting a scalar matrix with diagonal elements equal to 11. Now after this we have to find the adjoint A into A, and this is giving us the same result as 11 scalar matrix 11 0 0 0 11 0 0 0 11. Now our last step is that we have to find the determinant A into identity matrix. Now determinant A, as we have obtained earlier, was equal to 11, and identity matrix will be of the same order as the matrix A, and matrix A was our order 3 by 3, so we will take the identity matrix of order 3 by 3, and that is again giving us the matrix 11 0 0 on multiplying this 11 to all its term 0 11 0 0 0 11. So we can say hence A into adjoint A is equal to adjoint A into A, and that equal to determinant A into identity matrix. Now from question number 5 to 11, we have to find the inverse of each of the matrices if exist. Now if exist, that means first of all we have to find the determinant A, and if determinant A is not equal to 0, then only we can say that the inverse of a matrix exists, and then we will find its inverse. That means we will find the inverse of the matrix only non-singular matrix. Now inverse of singular matrix cannot be obtained. Here I am solving question number 10. A square matrix A is given to us. We have first of all we have to see whether this matrix is singular and or non-singular. Now for that, determinant A. Now here I am expanding column 1. So determinant A will be equal to minus 1, 1 plus 1 into 1, determinant of 2 minus 3 minus 2 4, then plus minus 1 raised to power 1 plus 2, sorry this 0 is 2 plus 1, first element of second row, into 0 into determinant of non-eliminating row and column, will get minus 1 2 minus 2 4 plus minus 1 raised to power 3 plus 1 into 3, determinant of minus 1 2 2 minus 3. Now this will give us minus 1 raised to power 2 will be positive, 1 into 1 will be 1, into determinant of 2 4 is 8, minus 2 into minus 3 will be plus 6. This second will be 0 at it is being multiplied by 0, and third will be minus 1 raised to power 4 will be positive again, 3 into 3 minus 4, and that will be equal to 2 plus 3 into minus 1, 2 minus 3, and that equal to minus 1, which is not equal to 0. So we can say A is a non-singular matrix, and is invertible. If the determinant of A comes as 0, then that will be a singular matrix and will be not invertible. That means we cannot proceed further. But here it is a singular matrix, so we will find its inverse. After finding the determinant of A, our next step is to find the cofactors of A. I have already obtained the cofactors of A, and these are 2 minus 9 minus 6, 0 minus 2 minus 1 minus 1 3 2 row wise. Now in our third step we will find out the adjoint A, and adjoint A is equal to the transpose of cofactor of A. Now cofactor of A were already obtained, so we will interchange the rows and columns of cofactors of A to find the adjoint of A. Now first row of cofactor will become the first column of the adjoint A, and second row will become the second column, and third row will become the third column of the adjoint A. Now we have to find the A inverse. Now A inverse is equal to 1 upon determinant of A into adjoint A. Now 1 upon determinant of A was minus 1, as we have obtained in step 1, into adjoint A, and adjoint A is given here. Now on multiplying each term by 1 upon minus 1, we will get the value of A inverse, that is minus 2, 0, 1, 9, 2, minus 3, 6, 1, minus 2 row wise, and this is our answer. Now here in question number 12, matrix A and B are given to us, and we have to verify that AB whole inverse equal to B inverse A inverse. For that, first of all, we will multiply matrices A and B and then find their inverse, and later on we will find out the inverse of A and B, and then we will multiply B inverse and A inverse, and these two will give us the same result. That means AB whole inverse equal to B inverse A inverse. And always keep in mind that for any two square matrices, AB inverse is always equal to B inverse into A inverse. Now here in 13 to 16 questions, we have to solve the given equations and then find out the value of A inverse. Now here I am doing question number 15. Here matrix A is given to us, and we have to show that A cube minus 6A square plus 5A plus 11I equal to 0, and hence we have to find A inverse. Now, matrix A is already given to us. We have, first of all, we will find out matrix A square. Now A square will be equal to matrix A into matrix A, and this is giving us a matrix whose first row is 4 to 1, second row is minus 3, 8, minus 14, and third row is 7, minus 3, 14. Now we will find out the value of A cube. Now matrix A cube will be equal to A square into A. Now value of A square was already obtained, and value of A is given to us. And on multiplying A square by A, we are getting the matrix A square as 8, 7, 1 as the first row, minus 23, 27, minus 16, 9 as the second row, and 32, minus 13, 58 as the third row. Now we had to prove that A cube minus 6A square plus 5A plus 11I equal to 0. Therefore we can say that A cube minus 6A square plus 5A plus 11I will be equal to, now we will put the values of A cube, A square, which we have obtained earlier, value of A which was given to us, and identity matrix. Now we will take the identity matrix of the same order as that of matrix A. So here we are taking the identity matrix of order 3 by 3. Now 6A square, we will multiply the whole matrix A square by 6. All the elements of A square by 6, and all the elements of A by 5, and all the elements of identity matrix by 11. Now adding these matrices, we will get a matrix with its all elements equal to 0. That means this matrix is equal to the O matrix or 0 matrix. So we can say that A cube minus 6A square plus 5A plus 11I is equal to 0. Now we also have to find the value of A inverse. Now we will use this equation to find the value of A inverse. Now as it has been proved that's a cube minus 6a square into 5a plus 11I is equal to 0. So we will make use of this one. Now on post multiplying all the terms of this equation by a inverse, we will get a cube into a inverse minus 6a square into a inverse plus 5a into a inverse plus 11I into a inverse equal to 0 into a inverse, and 0 into a inverse will be equal to 0. Now here we can write a cube as a square into a, and that will be multiplied by a inverse. Now similarly 6a square can be written as a into a inverse was already there, a into a inverse we will take together. Now 5 into a inverse, and that equal to plus 11 I a inverse equal to 0. Now as we know that a inverse a is equal to I, and any matrix multiplied by identity matrix give us the same matrix. That means a square, a into a inverse will be I, a square into I will be equal to a square minus again a inverse a or a into a inverse will be equal to I, and a into I will be a plus a into a inverse will be equal to I, so that will be 5I plus 11 I into a inverse will be equal to a inverse equal to 0. Now that means 11a inverse will be equal to a square minus 6a plus 5I minus a inverse 11a inverse will be equal to a square minus 6a plus 5I. On taking this 11a inverse to the right hand side, now this will give us a inverse equal to minus 1 upon 11 into a square minus 6a plus 5I. Now we will take this as equation first, and we will find out the value of a square minus 6a plus 5I. On putting the values of a square, a and I in a square minus 6a plus 5I, we are getting the value of a square minus 6a minus 5I as a matrix whose first row is 3 minus 4 minus 5, second row is minus 9 1 4, and third row is minus 5 3 1. Now from equation first we can say that a inverse is equal to minus 1 upon 11, 1 upon minus 11 into, now value of a square minus 6a plus 5I was 3 minus 9 minus 5 minus 4 1 3 and minus 5 4 1. Now this will be equal to, now we can divide it by minus 11, but here the elements of this matrix are not divisible by 11, so we can multiply it by minus 1 to get minus 1 upon 11 into minus 3 4. Now on multiplying the all the elements of the matrix by minus 1, so this 5 9 minus 1 minus 4 5 minus 3 minus 1, and this is the value of a inverse.